una conferenza da parte del professore Emmanuel Trelat e un rinfresco, che è sempre una cosa gradita, e poi ci saranno presentate le attività di stage. Quindi ecco, mi faceva piacere salutarvi a nome del direttore del Dipartimento di Fisica, la professoressa Rossana. Do la parola a Alessandra che presenta il master e poi...
ma forse non serve la presentazione del master, che abbiamo già fatto all'inizio, all'introduzione dell'anno accademico. Vorrei... ok, perfetto, allora...
si scelgono sempre
prima di cedere la parola a Giuseppe per la presentazione della conferenza di oggi, il professore Emmanuel Trelat, vi vorrei segnalare che abbiamo attivato un nuovo sito internet che si chiama Astrodynamics Vergata, sul quale potete trovare questa conferenza, d'accordo? Anche che viene videoregistrata, e anche altre conferenze che faremo nell'ambito dell'astrodinamica, del master, dei progetti europei e così via. Il sito è stato realizzato da Giancarlo Baglioni, il logo analogo a quello del master da Cristina Giorgilli. Come detto prima da Francesco, il programma di oggi riguarda la conferenza, poi il rinfresco e la presentazione delle attività di stage, in quest'ordine. Purtroppo il dottor Ettore Perozzi non potrà essere presente per motivi personali, ma avremo un'altra presentazione da parte, se non sbaglio, del dottor Quozzo e della sua società. E qui vedete la lista secondo l'ordine in cui sono arrivati, ci sono arrivate la richiesta di presentazioni. Io prego tutte le persone che non hanno inviato per email la presentazione di darcela durante il coffee break, in modo tale che possiamo poi partire. Come vedete sono 10 minuti esatti per ciascuno, non possiamo andare oltre, e quindi è importante che le presentazioni siano già tutte pronte. Sul sito di Astrodinamica trovate l'indirizzo, è l'ho scritto qui, www.mattuniroma2.it/astro con la maiuscola. Trovate diverse pagine che sono quelle delle persone, che includono anche la dottoressa Marta Ceccaroni, la dottoressa Paez, Ugo Locatelli, Giuseppe e me e altre persone. E c'è una sezione dedicata al podcast in cui mettiamo, naturalmente tutto fatto da noi, quindi scusateci se siamo un po' artigianali, ma ritrovare queste conferenze così come altre conferenze sono state date nei giorni scorsi. Trovate anche progetti, meetings ed altre informazioni che mi auguro possano essere utili. A questo punto cedo la parola a Giuseppe, così iniziamo con la presentazione.
Grazie. Bene, come i nostri studenti sanno, abbiamo dedicato molto spazio alla dinamica del volo spaziale, e all'interno di questo range molto ampio di argomenti, l'argomento del controllo, della teoria del controllo, è particolarmente importante, e quindi abbiamo pensato che questo potesse essere un argomento di interesse per una audience più ampia, quindi abbiamo pensato di organizzare anche questo evento. Now I think that I can switch to English because our guest comes from Paris. We have the pleasure to have the Professor Emmanuel Trelat, who is a leading researcher in the area of the control of dynamical systems. He's from the University Pierre and Marie Curie from Paris, Paris 6, and he's had several awards on his activity of research. Especially, he is the recipient of the Felix Klein Prize in Mathematics that he earned 2 years ago. Let me catch the occasion to thank Professor Cannazza for the opportunity to have him here. And so, okay, I introduce Emmanuel, and he will explain us that everything is under control. Please.
Thank you very much. Well, not everything is under control, I get reassured.
Almost.
But anyway, we will try to do as we can. So, do I have to reduce it? Yeah, okay. So, mainly in this talk, I will focus on control applications to aerospace problems, but let me, however, make a short introduction and a short general introduction of what is control and what are the main questions that can emerge in control theory. First of all, let me recall that control theory is a branch of mathematics which is whose objective is to steer a given control system to some from some initial configuration to some final configuration, possibly by minimizing some cost or maybe by stabilizing some trajectories in order to make them robust to some external disturbances or whatsoever. But mainly it's a subdiscipline of applied mathematics in which you are given some system, abstract system for the moment. In few time the system will be in aerospace, of course. I will focus on aerospace. But it is an abstract system on which you can act by means of a command, a control. And by choosing a control guidance law, you would like to steer the control system from some initial point to some final point or some final configuration. This is the first question that can emerge in control theory. This is the question of controllability. But then imagine that we are able to provide a positive or maybe a negative answer to that question. Then most of the time the second question that can emerge is the question of optimal control, because most of the time if we are able to steer the system to some final configuration, most of the time there is an infinite number of ways to go there. For instance, when you are making a parallel parking with your car, there is of course an infinite number of ways of doing it. And some of them are quite good and some of them are not good, let's say. Okay? There is an infinite number of ways, and among this infinite number of ways to realize the controllability problem, maybe you would like to select, to determine some of the trajectories which moreover minimize or maybe maximize a given criterion. This is optimal control. Okay. And so now imagine that also mathematically this question has been solved. Then quite often the question that arises is the question of stabilization. So stabilize, everybody knows probably what is stabilizing, but just in one word, stabilizing is making this. Okay, you have maybe here. For the future, you have an inverted pendulum with a stable configuration here, an unstable configuration here, an unstable point, and you would like, with an action of your hand, you would like to stabilize it around this unstable point. Okay, so this is stabilization, and from the practical point of view, this is also very, very important, because most of the time in the reality you have some perturbations. I mean, this equilibrium is unstable, but if there is a very, very small perturbation, then the equilibrium is not stable and will go to its stable configuration. So because of these numerous errors that you can have in the model, the stabilization is a very important issue most of the time in order to make realistic, for instance, one guidance law that you would have achieved with some optimal control. Okay? There is also an important question emerging in control theory that I will not talk about. This is the issue of observability, which is mainly concerned, say, with signal theory and so on, which consists of reconstructing the full state of a system from some partial data. I mean, when you receive an SMS or something like that in your mobile phone, the signal is not perfect. It is maybe it is partial. There are some errors, and by observing, by measuring only one part of the state, you would like to be able, however, to get a reconstruction that has to be as good as possible from these partial data. Okay, so let me also recall that control applications emerge in many, many disciplines, actually most of the disciplines that you can imagine. It is very easy to provide many examples in mechanics. I talked about making the parallel parking of a car, that is steer a car with by turning the wheels and also by acting on the pedals in order to brake and to, well, control a car. Okay. From the conceptual point of view, it is not very different to control a car or maybe to control a rocket or a satellite. Okay, maybe I'm exaggerating a bit, but conceptually, mathematically, it is not so much different. You have to deal with some equations and to turn them into some desired objective. There are enormous applications of control theory to robotics. When you would like to act on some, say, robotic arm remotely, for instance, in order to make some surgery, why not? But there are many other disciplines in which you can use some control and some mathematics which are related with controls. For instance, I talked about observability issues, and of course in electricity and electronics it is pretty much used. It's needless to say that. Also in chemistry, if you think of petrochemy, for instance, petrochemical industry, in which you have some petrols that you would like to steer from an initial configuration, which is the petrol, to some final configuration, which is, for instance, the kerosene that we have in the plane. Okay? Then you can act on the petrol by acting on the temperature. Then in that case, the temperature will be the control. It's a thermostatic control that you act on in order to steer the chemical reaction to some final desired state. It is also, of course, a controllability problem. To provide still one more example, let me say that there is a strong emergence of optimal control in medicine. For instance, currently I've been working in medicine on chemotherapy. The objective is to act on a population of cells. Some of them are tumor cells, some of the other cells are healthy cells, and you would like to act with some drugs, to choose an adapted chemotherapy in order, of course, to kill, at the end of the day, to kill the tumor cells as good as possible in function of a certain criterion. Okay? Of course, in that case, the problem is to be able to have good models. Everybody knows that in order to make some good optimal control application, then you have to have available some good models. This is a problem. This is a problem in economics, for instance. Okay, but let us focus now, from now on, and for the rest of the talk, on some applications of control theory to aerospace problems. So in order to start, let us start with a very usual problem emerging in aerospace. This is the problem of orbit transfer of a satellite. So you have, say, a satellite on which you can act, for instance, with solar panels, for instance. And this satellite, you would like to transfer it from some initial orbit, for instance, a very eccentric and low orbit, why not, to some final orbit, I don't know, for instance, the geostationary one. And the characteristic of this problem, say here, is that you would like it to be equipped only with low thrust, either motors or maybe some solar panels. I mean, the thrust that with which you can act on the satellite will be assumed to be very small, of the order, for instance, of 0.1 Newton. Just to give a flavor of what is 0.1 Newton. Oops. No, I don't see any sheet of paper, but more or less it is the force that you need. No, to make move with your finger a sheet of paper. Ah, thank you. Maybe this is applied mathematics. Exactly. So more or less 0.1 Newton is the force that I need just in order to make move a sheet of paper like that. Okay, and with only such a low thrust, you would like, however, to be able to steer your system from an initial orbit to a very, very far final orbit. Of course, we are in the space, so it is possible on Earth. So let us keep in mind that the thrust will be low. Then mathematically, and from the mechanical point of view, the control system that is underneath is just the controlled Kepler equation. So this is the usual Kepler equation, in which there is an additional thrust, which is the control. So capital F is the control, and as I said, its maximal amplitude is less than 0.1 newtons. Okay, and you would like to steer this satellite to a final orbit, say, for instance, by minimizing the time of transfer, maybe, or if it is equipped with some motor, you would like to minimize the fuel consumption. This is another kind of standard problem. So probably, as many of you know very well, it can be indeed written in the form of an optimal control problem. And here is the class of optimal control problems that we are going to deal with throughout the talk. In the previous case, taking the position plus the speed, this gives you the state in dimension 6. The control is the external force applied to the satellite. And then you have a classical optimal control problem in finite dimension. Throughout the talk, I only focus on finite dimensional optimal control problems, not infinite dimensional. So in the form of a control system, classical one, x dot equal f of x and u. U is the control, is subject to some constraint. And you would like to steer the system, say, for instance, from some initial point, or more generally from some initial configuration, to some final configuration by minimizing some cost functional, which is here represented in terms of an integral, the integral of some function. Okay.
What is F0?
F0 is the instantaneous cost. For instance, if you would like to minimize the time, then you can take F0 equal 1. And if you would like to minimize the fuel consumption, for instance, then you can take F0 equal to the norm of U. I mean, in that case, the cost is the L1 norm of the control. And there are many, many variants like that. Okay. So let me recall that the milestone in mathematics of the optimal control theory is the well-known Pontryagin maximum principle, emerging at the end of the 50s, according to which, so it gives you a first order necessary condition for optimality, which will allow to compute the optimal trajectories. It says that every minimizing trajectory x, say associated to some control, to some optimal control u, must be the projection of so-called extremal, that is a quadruple, xp, p naught, u, where p is the so-called adjoint vector. And by definition, an extremal has to be the solution of an Hamiltonian system, which is written here, where h is the so-called Hamiltonian of the optimal control problem. And moreover, the control u, the optimal control u, must maximize the Hamiltonian along the extremal, that is along the horizon of time. Okay. Let me also recall that such an extremal is said to be normal whenever the P0 component, which is the dual component of the cost, is non-zero, and abnormal otherwise. Okay. You can also see the adjoint vector in terms of a Lagrange multiplier associated with the optimal control problem. So it gives you a flavor on the sensitivity of the optimal control problem with respect to the components of the state. Okay, so the adjoint vector is some Lagrange multiplier for some reason that I will not go into detail. Let me just recall that the maximization condition of the Pontryagin maximum principle is classically used under some general assumptions in order to express the optimal control as a function of the state and of the co-state or adjoint vector. Okay? Believe me, it has to be made explicit. And then you can plug this expression into the previous Hamiltonian system. And then you get, at the end of the day, you get a completely autonomous system in x and p in which the control disappeared. So this is what says the Pontryagin maximum principle. It says exactly that you do not have to search the optimal trajectories among all possible trajectories, but only among this set of extremals. This is the enormous reduction operated by the Pontryagin maximum principle. Okay, it says, in mathematical terms, in more geometric terms, it says that the minimizing trajectories are to be sought among some geodesics. Okay? These are geodesics. And now what we are wanting to do is we would like to select a trajectory which is, say, going from x0 to some point x1. But okay, we are not, it is not a classical Cauchy-Lipschitz problem. In order to solve this problem, we have actually to find what is the good initial joint vector, P0, which is the unknown, so that when you solve this Cauchy problem, I mean with the complete initial condition in x and p, then the P0 has to be sought such that indeed the x of t will be equal to x1. It is the well-known shooting method, which consists of determining what is the good initial joint vector. It is exactly like when you shoot an arrow. Imagine that you are shooting an arrow. This is an arrow. And I'm trying to shoot, say, this point. And so I'm here. I'm at x0, and I would like to shoot the point x1 with an arrow. So what I do here, when I'm here, I am choosing the slope, the initial slope of the arrow. I am choosing the initial joint vector P0. It is exactly that. And I am trying to determine what is the good initial slope so that when I shoot the arrow, or when I integrate the ODE, then at the end, I will shoot exactly the point x1. You can see that it is a matter of tuning what is the good initial joint vector. So it means that mathematically, and from the numerical analysis point of view, you have to solve an equation, which is exponential of p naught is equal to x1, where the object here, the exponential, is the classical exponential mapping, which is exactly the integration of the extremal system. Okay? This is the contents of a shooting method, which from the numerical point of view is nothing else but integrating an ODE and solving a nonlinear equation with a Newton-like method. Okay? Okay, and just to conclude with the PMP, the Pontryagin maximum principle, let me stress that the PMP is only a first-order necessary condition for optimality, and nothing else. It is just saying that some derivative is vanishing, and that's all. It doesn't say that conversely, the extremals that you are computing are indeed minimizing. It does not say that. In order to say that, we have to look for, like in classical optimization, we have to look for second-order conditions, and this leads to the well-known theory of conjugate point, which is much more difficult, and on which I will not comment here. Of course, maybe this is not necessarily the first method that you have seen in order to compute some optimal trajectories. It is one method, but it is not the only one. There are other numerical approaches in order to compute optimal trajectories. Currently, we make the classical distinction between the so-called indirect approaches and direct approaches. So what does it mean? In the direct methods, you do not care about applying the Pontryagin maximum principle, but given the optimal control problem at the beginning, you immediately discretize the whole problem. I mean, you discretize the ODE, you discretize the cost, and then you come out with a classical optimization problem with constraints that, of course, you can solve by choosing an adapted numerical method, just like gradient method, KKT, blah, 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 dual methods. And this gives you the whole set of so-called direct methods. In brief, in direct approaches, you first discretize and then you dualize. Whereas what I showed you on the previous slide, the shooting method, is exactly the converse. You first dualize, because you first apply a first-order necessary condition, and then you discretize. It is exactly the converse. And here, for the mathematicians, there is an enormous challenge, very interesting and unsolved, of knowing whether or not this diagram commutes? And the answer is no. And so it is a good news for us, but a bad news in general. Okay. But it is an open problem that I will not comment here. Okay, what I would like to comment from now on is that we are speaking about aerospace problems, and in aerospace problems, in most aerospace problems, that I know actually, at least, in general, we privilege the use of shooting methods. Why? Why? Because, first of all, a shooting method is a Newton method. So when it converges very quickly and very efficiently. I mean, with a very, very good accuracy. And when you are steering some satellite very, very far, and that you need a precision of several millimeters, in general, you cannot hope to reach such a precision with a direct method, or at least it can be very, very challenging. So this is why in aerospace applications we tend rather to use shooting methods, because they can offer an unbeatable numerical accuracy. Okay? But now, since it is a Newton method, as you know, it is very difficult to make converge, because it is extremely, much more than direct method, extremely sensitive to the initialization. So the main problem is, okay, but how to initialize a Newton method? Just in order to illustrate that, I was a bow shooter, an arrow shooter. Okay. Now, okay, you can say here I am in the same plane and I need only to tune only one parameter. No, but it's not true. Now I will close the eye, I will turn in many times. At some point, Pierre-Marco will tell me stop. Please, Pierre-Marco. Stop. Okay, and you can see that it's not. No, you are cheating. And you tell me now shoot. Okay, I will shoot, and the numerical method will never converge. Why? Because the initialization is far from good. Okay, if you would like the numerical method to converge, you need to initialize somewhere here. Okay, and then to tune so that indeed I will reach the final point. Okay, so now even we are not in the R3 in aerospace, we are at least in R6 or maybe more. Okay, so imagine that if you do the initialization blindly, I mean without having a guess, there is no chance that the method will converge. So it is very, very difficult and sensitive. Fortunately, since the 60s, the mathematicians worked a lot on the problem of initializing a shooting method, and they found that indeed it can be brought to real applications, but at the price of combining the shooting method with more or less elaborated techniques. So some of them are written here. I wrote a survey actually on that kind of problem. And in the sequel, I will talk only on two of them. I will talk on continuation methods and also on the use of dynamical system theory. So let me figure out what is the picture of continuation methods. It's very simple to understand and very intuitive too. Let us come back on the optimal control problem of the beginning. That was making the orbit transfer of a satellite with a low thrust. Okay. So when you code that problem in MATLAB or in Fortran or whatsoever, you immediately realize that the main problem in the orbit transfer problem with low thrust is the fact that you have a low thrust. I mean, it's completely obvious. If the thrust was strong, then you would have much controllability of the problem, and you feel that implementing a shooting method with a strong thrust would have a good chance to converge. The stronger the thrust is, and indeed, the larger the domain of convergence of the shooting method is. It's quite obvious. But now, since the thrust is very, very low, also the domain of convergence of the shooting method is very small. So it means that if you initialize just by chance, it will never converge. So it gives you the idea, of course, of cheating. We cheat, of course, we always cheat. And here, the cheating consists of making as if the maximal thrust, capital F max that you have here, was strong. Okay? So you cheat. You start with a rather strong thrust. Oh, well, it is not even so strong here. You take a 60 Newton. It is not strong. But anyway, it is much stronger than what you are allowed. And then, starting with such a value of F max, the domain of convergence of the shooting method is much larger, and it is much easier to initialize successfully a shooting method. So you start from this very extremely simple remark, and then what you will do is to decrease step by step the value of F max. This is a continuation. In other words, you are not solving only one shooting problem, but a series of shooting problems in which, at every step of the iterative process, you initialize the new shooting problem with the successful solution of the former one, and that's all. And you decrease, step by step, the value of F max up to down to some very, very low values. And it works. But why it works? Why it works? Here, maybe it is interesting to analyze very simply what can happen. Actually, what you are trying to solve is that kind of problem. You are trying to solve a shooting problem. So to solve an equation, exponential of P naught is equal to x1. But now, inside this equation, there is one more parameter that you make vary. This is the F max. This is the maximal thrust that you make decrease step by step. So F max is not a good name of a parameter. In mathematics, a parameter is lambda. So let us use lambda. And now it's very clear. Because now you have to solve an equation depending on an additional parameter, which is lambda. Okay? And so for every value of the parameter, you solve this equation. What you expect is that the solution P naught of lambda will evolve in a continuous way in function of lambda, because the problem evolves continuously, and you hope that it will be the same for the solution P0 of lambda. And it is indeed the case if you are assuming appropriate assumptions that are very natural on the problem. Actually, to be precise, the two assumptions that you need and which will ensure that the solution P0 of lambda evolves in a good way, in a nice way, in function of lambda, these two assumptions are the following one. The first assumption is the absence of conjugate points, so that I mentioned in a former slide, which is very easy to test numerically, so it is almost for free. And the second assumption that you need is much more geometric and much more difficult to check. It is the absence of abnormal minimizers, so which are these extremals appearing in the Pontryagin maximum principle, for which the component P0, the dual component, is equal to 0. And this is much more geometric, but anyway, most of the time it holds true, so it's a good news too. Okay. And under these assumptions, indeed, the continuation method does work. Another picture that you can figure out in order to see what is a continuation is that you have some connected components over the set of optimal control problems, say, and you are traveling into such or such connected components, step by step. This is continuation. It is connectedness, that's all. But very, very useful. For instance, one application in which we use strongly continuation or homotopy methods is the recent work I did with the industrial EADS Astrium, now becoming Airbus Defence and Space, since the beginning of the year. For these industrials, actually, what I did is a new software which is achieving, whose objective is to compute automatically and instantaneously what is the optimal trajectory in order to steer an Ariane launcher, say, from an initial orbit to some desired final orbit. It has to be done automatically, that is without any human intervention, and instantaneously, actually within 1 second. Okay? And actually, we could do it indeed with the use of Pantry-Hagin approach, which is the only way of reaching such a speed in the execution of a software. You cannot do it. You cannot do it with a direct approach. It is completely impossible. Okay? Actually, for the story, the software that EADS used up to now was a software done in the 60s. It was done with a direct approach, at least most probably because they lost the sources, actually. And for certain configurations, the computation could take up to 3 weeks. You see. So you see the gain that we could bring in the problem just by using a Pantry-Hagin approach, and some quite elaborated mathematics, however, inside. For instance, we use one funny continuation. It is funny in some sense because, you know, the Earth is round. Okay, but this is a problem. Because imagine 1 second that the Earth is not round, but flat. Okay. If the Earth is flat, then computing some transfer orbit is much easier. You can solve easily. It's an easy exercise. Okay. So start from this simple observation, solve the problem for a flat Earth, and then step by step introduce the continuation of the Earth. And so it is quite a funny continuation in order to recover what can be the true model with a round Earth model. This is one of the tricks that we use, and actually that I am allowed to speak, because otherwise I am not allowed. Okay. Okay. There is another very urgent challenge to be solved. As you are probably sensible to that challenge, Alessandra is working on it. It is the challenge of removing the debris in the space. Probably you know that the sky, the sky over our heads, is a real garbage. Actually, it is full of debris which are left by former satellites of the 60s, of the 70s, maybe of the 80s, which were dead satellites, which did not come back on Earth because it costs a lot, and sometimes it is impossible, and so they were let, maybe in low orbit, maybe also around the geostationary orbit, and step by step they enter in collision, the ones with the others, and it creates millions of debris, like in the movie Gravity. So it is very, very dangerous. Actually, there are thousands of debris that are catalogued whose size is more than 10 centimeters. Some of them have the size of a bus. So they are enormous. And they are extremely dangerous, of course, because if they enter in collision with our satellites, then they can break the satellite. So it's extremely dangerous. And not only that, it costs a lot. That's the main problem. There are almost millions of debris which are smaller, say between 1 and 10 centimeters, and probably other millions of smaller ones that cannot be catalogued at all, but that are also extremely dangerous. And so, actually, it was last year or 2 years ago, I don't remember, that we have reached a critical point. The critical point means that because of the exponential explosion of the debris, it has become very critical to do something. So we have to remove the debris out of the space. Otherwise, the problem is that, and most probably actually, within few years we won't be able to launch new satellites. Why? Because it has become too much difficult to avoid the debris when the satellite is on a given orbit. And after that, the collisions cannot be avoided, and so you cannot launch new satellites just because they will be broken very quickly. So there is an enormous financial stake, and so there is actually there is a good and a bad news. So the bad news first, the bad one. The bad news is that we do not know how to solve the problem. So it's a danger, because probably more in Italy than in France, but we are quite fond of these small materials, and it is not clear whether or not in few years we will be able to use them. So now the good news. Well, the good news is the same. We do not know how to solve it. And so it depends on the point of view. For the mathematicians, it's a good news, because we like the challenges. We like the unsolved problems. But no, I'm laughing, of course. It's a double bad news. No, we do not know. We do not know, I mean, we do not know how to solve it completely and efficiently. To now, it is very, very complicated. Okay. So probably there are many, many works within the forthcoming years, and we would like many brilliant young researchers to come and work on that kind of subject. For sure, there will be some work. Sure. Okay, let me come to the final part of my talk, which is rather connected, not much with optimal control, but rather with stabilization. It is on the three-body problem and on its application to aerospace problem. So let me briefly recall what we call here the circular restricted three-body problem. It is just the dynamics in the space where you have two very massive bodies, such as the Sun and the Earth, for instance, and you have a third body whose mass is negligible with respect to the two first bodies, like a stone or a satellite. Okay? So you would like to represent what is the movement of a stone which is subject, say, to the attraction of the Sun and of the Earth. Okay, it is very well known. The equations can be written, okay, in the rotating frame, and it is known since centuries that these equations have exactly 5 equilibrium points that are called the Lagrange points. So it's very simple to understand. So now I need to cross. It is very simple to understand why there are 5 and exactly 5 equilibrium points. So imagine that you are in the rotating frame. Here is the Sun, the Earth, but they do not move. The frame is moving. So if you have a stone which is moving in these dynamics, then it is only subject, we will assume that, to the attraction of the Sun, of the Earth, and also to the centrifugal force, because the frame is rotating. So, okay, you can easily imagine that there is here, somewhere between the Sun and the Earth, an equilibrium point. I mean a point where you have to the left the attraction of the Earth, to the right the attraction, I said of the Sun, the attraction of the Sun, sorry, the attraction of the Earth, and also the centrifugal force. And at this point exactly, the three forces annihilate each other. Here also at the point L2, you have the attractions of the Sun and of the Earth to the left, and to the right you have the centrifugal force. So, okay, there is also one point here where there is this annihilation of force. Here also, the point L3. And here also the point, the equilateral points, L4 and L5, in which you have, for instance here, the attraction of the Sun, the attraction of the Earth, and here the centrifugal force, equilateral point. Okay. Actually, for the history, the 3 first points were discovered by Euler himself. But Euler did not discover the two remaining ones that Lagrange discovered, and so Lagrange won, and these are called the Lagrange points. Okay? But sometimes, however, the three first Lagrange points are also called the Euler points. Okay. So now, let us come to the mathematical issues, because the fact that there are some equilibrium points in these dynamics permits to imagine that you can steer some satellites or something there at this point, so that you can, for instance, explore the cosmos or look at the cosmos. For instance, think of the Hubble telescope. Maybe instead of placing the Hubble telescope where it is, it would be nicer maybe to place it, for instance, here or here, over there. Why not? It's a good place. So it is good for the observation of the cosmos. So now we have, first of all, to study what is the natural stability properties of these points. And this can be done with already quite fine mathematics, because it is not the direct linearization theorem, the first linearization theorem, but already you need a bit of KM theory, just a bit of. But the fact is that, so actually in the Sun-Earth configuration, the three first Lagrange points are unstable, and the two others, L4 and L5, are stable. So what do I mean? I mean that if I put a stone here, it doesn't stay in the neighborhood of the L1 point. What it will do is turn around the Sun, then turn around the Earth, and so on. Same thing for the point L2. At the contrary, for the points L4 and L5, if I put a stone or a satellite, a Hubble telescope, here, then it will stay in the neighborhood of the point L5. And then I say, yes, good thing, because probably the stability of this point is a very good news in order to observe the cosmos. It is the first reaction. But again, good and bad news. Good and bad news, because, oh, yeah, this slide is just to say that in any three-body configuration, you have exactly 5 Lagrange points. For instance, in the Sun-Moon system, you have also 5 Lagrange points with the same properties. But look at, for instance, the system where the two massive bodies are the Sun and Jupiter. Then you look at the points L4 and L5. They are there. They are there, and indeed, they are very dirty sites. Dirty in the sense that in the neighborhood of these points, L4 and L5, there are plenty of stones, of asteroids. These are the Trojan, Trojan, I don't know how to say, asteroids. Because in the hazards of astronomy, maybe there were some stones coming in these potential. These are potentials, okay? These are stable potentials. So when a stone is coming down to a minimum of potential, then it remains trapped in the minimum of potential, and it cannot go outside. So bad news. Bad news because we cannot use actually these L4 and L5 sites in order to observe the cosmos, because there are too many. There is too many dust, or there are too many stones here. It is too much dangerous. So at the contrary, let us come back. Finally, bad news is always a good news for someone, like always. Finally, the instability of the point L1 or L2 is a very good news, because these sites are not dirty. There is no stone. There cannot be any stone. Or maybe I'm very unlucky, but okay. No, there is no stone because they will go outside. Okay. And so probably, at the price of making some stabilization, these are good sites in order to observe the cosmos. But you will have to pay a price. You will have to stabilize a satellite there. Imagine that you put a satellite exactly at the point L1, so it is exactly like an inverted pendulum. And so I have something to do in order to stabilize it. But, as you can see here, I have not much to do. So maybe only some solar panels with some low thrust can be enough in order to stabilize the Hubble telescope, for instance, or something like that, at the point L1. It's enough. Okay. So of course, it is well known, and these points are already used since many years. For instance, there are many objects, actually. There are many objects near the Lagrange points. For instance, near the point L1, not exactly near, but I will come to that point, you have the satellite SOHO, whose mission is to observe the surface of the Sun since 30 years, maybe? I don't remember. Okay. Near the point L2, so there are many other objects, but just a few examples. Near the point L2, you will have the next Hubble telescope, the James Webb Space Telescope, which will be put at the point L2. Ideal site, because it is at the opposite of the Sun with respect to the Earth, so to look at the cosmos, it is perfect. And just for the fun, I like to mention that in the 60s, the science fiction authors imagined that at the point L3, that is at the opposite of the Sun with respect to the Earth, it is invisible to us, they imagined that there was a planet, so it is completely unlikely, of course, there is nothing, but they imagined that there is a planet, the planet X, on which there are plenty of nasty inhabitants that were about to invade the Earth, and they were very nasty. So, okay, so it's funny because already in the 60s, the authors of science fiction had imagined some applications of Lagrange points, funny applications here. But by the way, it is a very, very bad series. Very bad. So I do not advise it. Okay, so now let us come back to mathematics. Now, near the Lagrange points, what is very interesting is that the structure of the dynamics is extremely rich, extremely rich. There are actually in the neighborhoods of Lagrange points plenty of periodic and also of almost periodic orbits. For instance, the ones that are the most well known are the halo orbits. The halo orbits are nothing else but kind of circles. You have a Lagrange points there, and around these Lagrange points you have a family of circles, halo orbits. Topologically, they are circles. Okay? But they are not, well, you have some families with 2 parameters actually for halo orbits, but you have plenty of other orbits. They are called Lissajous orbits, because in the neighborhood of Lagrange points you can find all these curves that you could study in mathematics years before. These are the Lissajous curves. For instance, there are curves that are drawing an 8, or a triple 8, or a quadruple 8, and so on. And also all the almost periodic orbits. They do all exist near the Lagrange points. All. You can meet, well, virtually at least, can meet all of them. And of course, they can have a use. They can be used for space missions. For instance, so now I will correct what I said for the SOHO satellite. Actually, the SOHO satellite is not put exactly at the point L1 between the Sun and the Earth. Why? Because if it was put more or less there, then we could not communicate with it because of the electromagnetic field that is sent by the Sun. We could not communicate. So what the engineers could imagine at that time was to make evolve the satellite SOHO on an enormous halo orbit. Enormous means of big amplitude, of large amplitude. So SOHO is evolving on a large amplitude halo orbit around the Lagrange point L1 in the Sun-Earth system. And of course, along this periodic orbit, again, you have to stabilize the satellite SOHO, because otherwise it would leave its periodic orbit. Another use that is more recent of halo orbit is the space mission of the probe Genesis 10 years ago. It was quite impressive because the probe Genesis could only use the very, very minimal amount of fuel consumption. It was very impressive. Just the fuel consumption needed to leave the Earth, and then more or less nothing. Nothing or almost nothing. It was very impressive. After leaving the Earth, it was put on a halo orbit near L1, and then at some point, just with a very small impulsion, it was put on what is called what is called the heteroclinic orbit, going to the point L2 at the opposite of the Earth, and then it was computed exactly so that it could come back on Earth without using or so little fuel. It was very impressive. Okay, so from that success, of course, it was tempting to think about all possibilities that are offered by the dynamics around Lagrange points in order to imagine space missions and also interplanetary space missions that are almost for free. So let me come to the last mathematical point that we will use. The point is that, so it's also a point of dynamical system theory. In dynamical system theory, you know, when you have some singular point, some equilibrium point, then in the neighborhood of this singular point, there are two manifolds, the stable one and the unstable one, like in a saddle point situation. There is an attractive dynamics and a repulsive dynamics, under some appropriate assumptions. So now, replace the singular point with a circle, with a periodic orbit, or maybe an almost periodic one. Imagine that it is like a singular point. Then it generates as well a stable manifold and an unstable manifold. So for instance, let me take an example. If you take a halo orbit, so it's a circle, so it generates a stable manifold, which is a tube which will connect onto the halo orbit, and an unstable one. And they have the property that we wish. I mean, if you put a stone inside the tube, so if you put a stone inside the tube here, then it will go through the tube, it remains inside the tube, it will cross the circle here, and go then to the unstable manifold. So actually personally I like to call them some gravity currents, because it is exactly like in the sea, in an ocean. In an ocean you have some currents, for instance the Gulf Stream, okay? What is the idea then? Imagine that you have no motor, and you would like to steer your boat without any effort from the west of Africa to the west of France, for instance. Then it is possible. You can do it with the Gulf Stream, because there is a current that is going to the north there. So if you are patient, of course you have to be patient, you take your boat to the west of Africa, you let it be, and you are able, if the current is deterministic enough, of course, you are able to steer your boat exactly to the west of France after maybe 6 months. Okay, but it is possible. Then it is exactly the same in the space. In the space, there are exactly such kind of currents, which are due to gravity, of course. These are not ocean currents, of course. These are gravity currents, but they can bring you for free, but very slowly, to some final point that you are exactly able to compute. Exactly able to compute, because in the space there is no perturbation, or almost no perturbation. So actually what you have to imagine, so it's an artistic point of view, it's not at all the result of any simulation, but what you can imagine is that the solar system, in the solar system there are plenty of tubes that can allow you to travel for free, for instance, between, say, the Earth and Jupiter. But you have to be patient. But it is for free. And all these tubes can be exactly computed, of course, with long time mathematical computations. It is there are plenty of difficulties underneath there. But the good news is that you are indeed able to draw a map, you are able to draw a cartography of the gravity current, which maps you a sort of a metro map. And like it was in Paris last Monday, actually, the metro is for free. The metro is for free. I mean, you do not have anything to pay. You do not need any fuel. When you are in some tube, you stay in the tube. And for instance, if you have thrown a stone here, then you know that after some months or maybe some years, I don't know, to compute, it will go exactly there. Okay, so it opens the way to the imagination, of course. But meanwhile, let us rather come back to Earth or to the Moon, because the interplanetary missions are probably not for tomorrow or even the day after. Probably we can play, we can imagine, but probably the next space mission is rather coming back to the Moon. Why? Because probably the Moon will be seen as an intermediate point in order then to reach Mars, probably. So what the engineers are going to imagine in the next years, very probably, is to build a lunar station, a station in principle at the north pole of the Moon, and this lunar station will serve as an intermediate point in order to bring some material to Mars. But Mars, well, I hope that some of you will be alive, but it's not so clear now. Okay, so in view of that, the challenge is now very currently, to be able to design low-cost trajectories, or at least trajectories having the lowest cost possible, that are steering us to the Moon. Actually, we have to design some cargo missions because we would like to bring much material to the Moon, and almost for free. I mean, there is no human inside. It can be robots. So we are not in a hurry. Instead of going to the Moon in 3 days, we can take 6 months. That's not okay. We are not in a hurry, but we would like to bring much material to the Moon. So it was more or less the PhD subject of one of my former students, Archambault, who is now engineer in Airbus, in EADS. And he worked during his PhD not on the halo orbits and on the tubes that are generated by the halo orbits, but on the tubes that are generated by these Lissajous orbits that are 8-shaped. There are Lissajous orbits that have the shape of an 8, like that. So you have to imagine that they generate tubes that are 8-shaped too, a bit like that. Okay. And here there was a very good surprise, which is not mathematical, unfortunately, but only numerical. I mean, we do not know how to prove it, but it's an observation. We computed the manifolds generated by the 8-shaped orbits in a long time, and contrarily to those of the halo orbits that are well known to be chaotic, these ones are not chaotic at all. They keep the same structure, they are stable within long time. So, except that they draw, these are the tubes in 8, okay? Except that they draw a very beautiful picture around the Earth, but we do not care. They draw, you see, they draw this picture around the Moon, and here the very good news is that they are going very close to the surface of the Moon. Actually, if you compute exactly what happens in the neighborhood of the Moon, you can see something like that, more or less, and you can see that their minimal distance to the Moon is only 150 and 500 kilometers, so it is very close. So what I mean here is that as soon as you are able to put some satellite inside such a tube, then you can go almost to the surface of the Moon for free. For free. And it is ensured because of the good stability in long time of these tubes that we do not know to prove. Okay, there is also here an open challenge. And so this is my conclusion. Let me maybe mention that, so we have some privileged contacts with EADS Astrium, so now Airbus. We try actually to launch a partnership with them and with the Foundation of Mathematical Science of Paris. So we will see. We'll see because we had already have many discussions, and it's not again the kickoff, but well, we hope that this time it will be the kickoff. And so what I would like to say is that there are many challenges. So there is, of course, the challenge of being able to design space missions that are almost for free and that will permit to explore the far solar system. Okay, But probably the most urgent challenge that I would like to insist on is the challenge of collecting space debris, because really, really, we need many people to work on that problem, because for the moment, okay, we have several solutions, but they are so rough, and we are so unready to face with the problem that we really need probably an international agreement in order to attack this problem. And this is really, really urgent. There is an enormous stake behind, and not only financial, of course. Okay, and I think I will stop here. Thank you.
Thank you very much. I think that there is at least material for a lot of movies, additional movies. Okay, we have time for some questions, for some discussion. No?
Well, there are several questions, of course. You touched several topics, and let me say a couple of questions. One is concerns the results about the manifolds around the collinear points.
Mm-hmm.
You mentioned the planar circular restricted three-body problem and the extension of Moser theorem, of Lyapunov's theorem given by Moser. Do you know any result about the elliptic problem? That is, the real situation is given by the elliptic problem. Because normally the ellipticity, the eccentricity of the orbits cannot be discounted. But I don't know now any result about the continuation of such manifolds into the elliptic case, which is, by the way, the right one.
Yeah. No, I do not think exactly now, except the works by the works that you know very well by Simo and so on.
Which are always in the circular case.
Indeed. No.
And then the second question concerns the space debris. Again, I don't understand very much where you use optimal control. That is, do you use it, for example, to tune some of the orbital elements, like the argument of 3G, or the eccentricity of the debris, to move it from one space to the other?
Well, actually, this problem can be seen, it is one of the possibilities, as an enormous binary, mixed optimization problem, in which, so you have a catalog of big debris, of many big debris. And first of all, in this catalog, the first question that you investigate is how to draw a path, so a path in a set of discrete points, which should be optimal for some criterion that you have chosen. And then, so this is the discrete part of the optimization problem, which is unsolvable, actually. It is a problem. And the second part is then, once you have chosen, say, two successive debris, what is the optimal way between the two of them? And here there is, say, classical continuous optimal control in order to design a classical trajectory. And this part is under control. The other part is not.
So not everything is under control?
No.
Okay.
Is there some additional question?
So it seems to me that there is a lot of room also for theoretical research. Usually one thinks that if you have a good numerical schemes and a lot of computing power, you can solve everything without bothering looking at the equations. But in this case, it seems there is a large need of ideas, new ideas. Could you?
Precisely, yeah. Precisely because probably the first reaction that anybody can have in front of such an optimization problem is, okay, let us discretize and let us see. Let us see what the computer is able to compute. Yeah. Maybe we are not in a hurry. We have months or years, and we can let the computer run. Okay, it is a naive way, of seeing, but here it happens that the problem is so much complex and there are so many fine possibilities inside that can only emerge from fine dynamical properties, that of course if you do that, if you do an enormous direct method, you cannot hope that it will work. It is far too rough, too rough. So you need to do even quite fine mathematics here in order to, how to say, to reduce the set of possibilities. And to reduce the set of possibilities, you really need to understand very finely what happens. So what happens in the neighborhood of the singular points, because here is the richness, as we know. In a dynamical system, where is the richness? Near the singular points, of course, always. Outside, there is nothing, it is straight lines. Okay? But so here we have to focus on what happens near the singular points. And here it is extremely rich. It's incredible. So we are very happy. And then understanding in a fine way what can be all these periodic and quasi-periodic orbits, invariant manifolds, brings an incredible number of new possibilities that could not be imagined and that certainly could not be reached with direct methods. It is completely impossible.
Just one last one. Is there any room for dynamic programming? Hamilton, Jacobi?
Yeah, I understood. It's not
Hard to tell.
It's not very clear. It's not very clear. Well, anyway, as you know, recently Asnazidani was able to apply with much success the Hamilton-Jacobi method to the problem of re-entry and also of launching satellites. It's very impressive. Actually, it was a surprise for me that there was so much recent progress in Hamilton-Jacobi in order to make this problem reachable. It was a good surprise. So maybe, but for the moment, I do not believe that this can be done for interplanetary missions, for instance, because you need to mesh a too big space. So it's not clear.
Okay, thank you again. We will resume in half an hour.
Giuseppe, magari ricorda di mettere la